Hello, everybody. Welcome back to Data Analysis. I'm your host, Professor Bassett. We have an exciting another lecture ahead of us today on simple linear regression. So let's go ahead and get started. So just a quick reminder of our primary course text, Truth About Linear Regression, Intro to Statistical Learning. These are going to be the references for these slides in case you'd like some more information. Okay, so let's just remind us where we've been. So in the first lecture, we talked about minimizing mean squared error when we were predicting y from some other random variable x, right? We talked about what does it mean to do optimal prediction. We defined mean squared error as some idea of optimal, right? This is population mean squared error. I mentioned this only because we've defined empirical mean squared error recently. And so we showed that if we want to minimize population mean squared error, then the best estimator to do so is the conditional mean y given x. Okay, and so we talked about in the last lecture this idea that y is some function of x plus epsilon, right? And so if we have a fixed x and we have some random noise term epsilon, we can actually write y, the random variable y, for some fixed x, as its expectation plus some noise. Okay, so this is actually kind of probably looks a little bit mysterious, but actually what I'm saying is we can just write any random variable x. Okay, let's say I have any random variable x. I can write it as a new linear combination of some constant mu, where mu is its mean, plus some random variable epsilon. So this thing is constant and this thing is random. And what I'm saying here is I can do exactly the same thing for the conditional random variable y given x, right? Where I'm basically rewriting so that we have x is some mean plus some random variable which is zero mean, because we basically pulled the mean out of x into this mu. Okay, so this is important because it actually relates to what we were talking about in the last lecture, where I talked about y is some function of x plus epsilon, because we'll notice that the random variable y is some function of x, this is this expectation, plus epsilon. Okay, and so this actually ties in, because what we're suggesting here is that this random variable y, so for any fixed x, we can write y, this is something random, as something, some function of the input x, okay, plus epsilon, where epsilon is mean zero because we're extracting the mean out of this random quantity here. In the same way, we could just write any random variable x as a mean plus a centered random variable. Centered, by centered, I mean it has mean zero. Okay. Okay, so this is just sort of actually connecting these two concepts that we saw in the first couple of lectures. We talked about when we're minimizing mean squared error, we want to find the conditional mean. We talked about you can have this y equals f of x plus epsilon, and the connection between the two of them is that if I have a random variable y and you fix me an x, I can write it as conditional expectation plus epsilon. And so then the name of the game is going to be, in order to minimize mean squared error, we actually want to find this expression, and this is going to be our function of x, this conditional mean. So as x moves, the conditional mean of y given x, this is our function f. Okay, so that's just a connection between the first two big concepts that we saw in the lecture, and we're going to be picking up and talking about this more in this lecture. So just make sure to sort of remind where we're at and fill in a little bit of the gap between the two lectures. Okay. So we also talked about in the last lecture that a good estimate f hat of this function f, so we know that this function f is the conditional mean if we want to minimize mean squared error. We don't necessarily have to minimize mean squared error in general, but for us this is true. So a good estimate f hat is one that has low mean squared error, and we talked about the bias variance decomposition. So the bias variance decomposition roughly says that mean squared error is a squared bias term, so that is expectation of that is the expected value of f hat minus f evaluated at x, okay, plus the variance term, so the variance of f hat. Okay, so it's sort of, the idea was that good mean squared error means if you have a good mean, if you have small bias and small variance, you're going to have a low mean squared error. And I'll just say this is approximate, right? Because I'm missing a very important term here, right? In the sense that we talked about that this mean squared error can be written as variance of f hat, right? That was one of the pieces that we had in the bias variance decomposition. The bias variance decomposition, or we had plus variance of epsilon, right? So both of these are sort of, I'm wrapping both of these up into the variance term, but the variance of f hat, so sort of how volatile our estimate is, that matters, and also the variance in the noise term also matters, right? Remember we talked about this is the irreducible error, and then this term and the bias terms are the reducible error. Okay, so and then just to continue the narrative, so we talked about, so this was sort of on the theoretical side. When we're talking about using data, we can approximate this population mean squared error, which is the sort of idea that we're using for a good estimator or our good prediction is one with low mean squared error. So we're going to approximate this population mean squared error with the empirical mean squared error, which is just the sample average form of it. And then in order to make sure that we're not overtraining, it's good practice to evaluate the empirical mean squared error on a testing set, which we hold out from the training process, if you remember that. So the idea is that we can, if we have too much flexibility on our model might hone in on details of the training set, which is the data used to build the model. So if we hold some data back, and we compute the empirical mean squared error on the testing set, then we have a better idea of how the model is going to generalize to new data. Okay. All right. So this is a quick one-slide summary of where we've been so far. So where are we going next? Next, we're going into simple linear regression. Okay. So simple linear regression predicts a quantitative response y. So remember, quantitative response. This is wrapped up in the word regression, right? For regression, we're predicting a quantitative or numeric random variable y, and the simple part of simple linear regression refers to the fact that we're using a single predictor x. Okay, so y from one predictor x. We've talked about generally the idea that we can have more than one predictor, but for now we're going to focus in on the one predictor case. Okay, so in simple linear regression, we assume that the f function, so that true relationship between y and f, or between y and x, is linear. Okay, so y, we assume this is an assumption, okay, is that y is some intercept term plus some slope times the predictor plus some noise term, epsilon, okay, and we assume that epsilon is mean zero for each x. Okay, so if you give me an x, mean of epsilon for that x is zero. Okay, why is that important? Because we're basically writing y as some function of x plus epsilon, where epsilon is mean zero, right? And the fact that this epsilon is mean zero ties us into the previous slide where we were talking about y is a conditional expectation plus epsilon. We want to estimate this conditional expectation. So basically, by making this epsilon mean zero, the linear term becomes the portion we want to estimate here, this conditional expectation, which is this function f. Okay, so just in the language you've introduced in earlier lectures, this is a parametric model. Okay, the reason it's parametric is that once you give me these two numbers, beta 0, beta 1, I completely know the structure of f, and yeah, so the name of the game becomes estimating these beta terms instead of just all possible functions f. Okay. So similar, and as per the statistics notation we've been using, we're going to know our estimates of these beta 0 and beta 1 terms as beta 0 hat and beta 1 hat. And one way to say this problem here more succinctly is that we're going to regress y onto x. That is, we're going to perform a regression estimating y from x. Okay. So yeah, simple linear regression refers to the fact that we have sort of this pretty simple linear relationship between y and x. All right, so some common assumptions here. Common assumptions are the first one. We've already assumed this on the previous slide, but I just want to sort of enumerate them. This is sort of the most basic assumption. The most basic assumption is that epsilon is mean 0 for every x. Okay, and if that's the case, then this term here is the conditional mean of y given x. Okay. We know that because we can apply the conditional mean to both sides. The epsilon will cancel because it's going to be 0, and we're left with the conditional mean of y is just this expression. Okay, so that's good for us. Why is that good for us? Is because if this term is the conditional mean of y given x, then it is the best predictor for y given x, and by best here I mean minimum mean squared error, right? So we talked about in previous lectures. We want to estimate the conditional mean. This will minimize mean squared error. We can do that if we know that the conditional mean of epsilon is 0 for every x. Okay, so this is good, but it gets even better. So I say we have these following assumptions in increasing order of preference. So by assumptions, right, we are going to assume them and get some properties out of these assumptions, which will allow us to make better conclusions in applied examples. Okay, so we are going to we are going to spend a lot of time focusing on how reasonable are these assumptions in the first place. So when I say these assumptions, you might think, okay, this is pretty divorced from practice, right? But basically what we want to know is, in a real world problem, we want to know which of these assumptions can we get away with. Which of these assumptions are supported by the data we have on hand, and if we can get away with more assumptions, we're going to be able to come up with stronger conclusions. Okay, so even though I say assumptions, it's not like we're just going to walk in and say, hey, I don't care what the real world looks like, I'm assuming these things, data, you better get used to it. We're going to be in some feedback loop where we're sort of saying we'd like to assume these things because we can make stronger conclusions. Does the data support making these assumptions? So just a caveat there. So the next assumption we will sometimes make, so this is stronger than the first one. The second assumption is is that the first assumption holds. Okay, so we have this conditional mean of epsilon given x is 0. And the second piece of it is that the variance of epsilon for each x, okay, so you fix me an x, I can look at the variance of the epsilon term. The variance is sigma squared, okay, for some fixed sigma squared, okay? This is important. So we'll sometimes refer to this as the constant variance assumption. Okay, so the first assumption says mean 0. The second assumption says epsilon is constant variance for all the x's. Okay, and there's a second point here, in that epsilon is uncorrelated across observations. Okay, so that is the covariance. The covariance of epsilon I, epsilon j equals 0 for I not equal to j. Okay, and here I and j refer to two different observations, right? So if you give me an x and a y, and you give me another x and another y, the epsilon terms that generated those x's and y's, they are uncorrelated, meaning their correlation is 0. Equivalently, their covariance is 0. Okay. So this is the second assumption, sometimes called the constant variance assumption. And the third and strongest assumption we'll use is 1 holds. Okay, so we always start with 1. And then epsilon, not only is it mean 0 constant variance, but is actually normally, i.e. Gaussian distributed. Okay. So notice in the second assumption we say mean 0 constant variance, but we don't say anything about the actual distribution of epsilon. It can be any random variable, which is mean 0 and constant variance. Okay, But with assumption 3, we're imposing a stronger assumption in that we're actually assuming its distribution. Okay, we're saying epsilon is normal, mean 0, variance sigma squared. Okay. And then we go even further. So instead of epsilon just being uncorrelated across observations, we assume that epsilon is independent across observations. Okay? And remember from the miscellaneous facts lecture that covariance 0 implies independence only in the case of normal random variables. So in the case of normal epsilons, this uncorrelated condition will give us independence. So once we've assumed epsilon, the epsilons are normal, this uncorrelated assumption in assumption 2 gives us independence, but we'll just be more explicit and just say we assume independence, right? We could write uncorrelated here, and because the epsilons are normal, these are equivalent, but we just write independent. Okay, so in English, we'll describe this as constant variance assumption. We'll describe this third assumption as our Gaussian noise assumption. So that is the noise term epsilon is Gaussian. Okay, so we're going to make a lot of use of these three assumptions. Please commit them to memory. Reference this slide as you need it. But yeah, there's going to be a lot of work that we can generate from the data based on these assumptions. Okay, so more lingo just in terms of introducing simple linear regression. So the observed y, so this is the true y, minus our predicted y hat, is called a residual. Okay, so remember in the case of our prediction in general, y hat is equal to f hat evaluated at our input point x. Okay, and so because our function f hat is this simple linear regression, we can actually write y hat is our estimated, so type over here, should be a beta 1. Right, y hat is our estimated beta 0 plus our estimated beta 1 times x. And the reason is that the form of f hat is, as we discussed, we estimate those terms, this intercept term and this slope term. Okay, so this observed y minus the predicted y is called a residual in general. Okay, and we denote these residuals by e. Okay, some texts denote them by epsilon hat. The epsilon hat for me is a little bit too much notation. I stick with the e, but I mention this because the notation is a little bit suggestive here. So epsilon hat is we can think of it as our estimate of our error term, right? And so what we're doing is, right, if we knew the true jump back. If we knew the true y, right, we could do y minus let me say this again. If our estimates of the beta terms were right on, right, so our beta hats were equal to the betas, we could do y minus y hat, which is this term, and just get epsilon, right? But because we're estimating this term here, we get y minus y hat, and it's not exactly epsilon. We call it epsilon hat because we're sort of plugging in our estimate there. Okay, so that that notation for the residuals, even though, as I said, I found it a little bit burdensome to have to write all the epsilon hats, I just use these e terms. But it's a interesting way to think of these residuals as the estimated epsilons. Okay, so epsilons and the residuals are different, and crucially so because we're plugging in our estimate here and we don't know the truth. Okay, so the mean squared error of our estimates, we can write them as, this is empirical mean squared error because I have a 1 over n. I'm taking a sample here. So this is 1 over n. So this is the mean squared error, so mean squared error. mean squared error, and this is, we're summing over our residuals. Okay, so this is, we can think about this as summation for some n observations. And what this is the mean squared, and we have a residual, but the residual, when we square the residual, this is the prediction error, right? So this is y minus the estimate. So this is mean squared error is, we're just writing mean squared error more compactly, right? Mean squared error of an estimate is you take the difference between the truth and the estimate and you square them and you take the mean. By writing it in this residual form, we're writing it more compactly. Okay. Quick vocabulary term, the residual sum of squares. Again, this is a vocabulary word which is pretty descriptive in terms of what it is. It is the sum of the square residuals. So if you see this, referring to the sum of the square residuals, whereas the mean squared error is 1 over n times the sum of the square residuals. Okay, so we're going to talk a lot about residuals. Residuals actually are going to be a big clue for us. By looking at the residuals, we're going to be able to see how these assumptions that I was talking about on the previous slide, if it's reasonable to assume these different assumptions that we listed here, the mean zero, constant variance assumptions, or Gaussian noise assumptions. But we will get to that in later lectures. So let's actually talk about how we find these estimates beta 0 hat and beta 1 hat. Okay, so remember, in general, we want to minimize mean squared error. This is the expected squared difference between the truth and our estimate. Again, in practice, we have no data, so we don't have this true expectation. We just have the sample average, or the empirical mean squared error. And so here, we can minimize empirical mean squared error instead. So I'm going to minimize over some dummy coefficients, b0 and b1. These are stand-ins for my beta 0 and beta 1. This expression. Okay. What this is the empirical, right? Because I'm working with data, I have observations x1, xi, and yi. And then this is the estimate of y for a fixed x using the slope b1, the intercept b0. So we will estimate these beta 0 terms by finding what is b0 and what is b1 as our estimate for beta 1. Okay. So how can we minimize this expression? Well, we're minimizing a function. It is a square, and square functions are smooth. We are going to find some critical points by taking some derivatives. Okay, so we're going to take partial derivatives with respect to b0 and b1. We're going to set them equal to 0. We're going to solve, and then we can use second derivative informations to verify that critical point that we found, that critical point, also called a stationary point, is indeed a minimum. Okay, so let's do it. Here's the expression we want to minimize in b0, beta, and b1. We're going to take the partial derivative with respect to b0. Okay, when we do that, what happens is we bring down the 2, obviously. We're going to take the derivative and the inside via the chain rule, and we actually have a negative b0, so a negative comes outside via the chain rule. Okay, so it's chain rule negative plus bringing down the 2 from the square. And then b1 is very similar. So what we do for b1 is we take the derivative of the outside again, bring down the 2. We're going to take now we're going to take the derivative of the inside as part of the chain rule, and we have a negative b1 xi. And so if we're taking the partial derivative with respect to b1. The negative xi is attached to the b1. So that thing is this negative comes from the chain rule, and this xi comes from the chain rule. This is the derivative of the inner function. This piece. All right. So we're going to set these both equal to 0 and solve for b0 and b1. When we set these equal to 0, we make an important distinction here, and that is we're no longer working with dummy variables. When we set them equal to 0, these are the equations that define our estimates for B0 and or our estimates for beta 0 and beta 1. Here we switch notations. This is important because we're saying instead of just some arbitrary function of inputs B0 and B1, we're saying these are our estimates once we set this equal to 0. Okay. So how do we solve this? Well, first we're going to cancel the -2 from each side. We're left with these expressions. And these equations here are called the normal equations. They get a special name because actually all of the properties of our estimates beta hat 0 and beta 1 hat come from these normal equations because these normal equations completely define the estimator in the first place. Okay, so these are called normal equations. How do we solve the normal equations? Well, we're going to do a little bit of algebra. So pretty standard notation, but I'm going to abbreviate sample means using this bar on top. So I have this sample mean of this quantity here, and I can push it through, right? So I can push through the sum. I can take the sample mean of y's, sample mean of this beta hat term, sample mean of this term, right? These terms don't depend on I, so they can go ahead and just come out of the summation. And I can do the same thing down here. Okay, so let's just start with this piece. What I get when I distribute this sample mean to the y, I get y bar. That's here. When I distribute the sample mean to this constant here, I'm taking the sample mean of something constant. All right, so summing up this piece n times, then dividing by n, I just get that constant. And then I do the same thing here, distribute the sample mean to this piece. The beta 1 can come out, and then I'm taking the sample mean of the xi's. So that is this here. Okay. And then I'll do the same thing on the bottom. So the sample mean here, this is the sample mean of x times y. Okay. So I'm going to take for each, so what this means is that, right, I have a bunch of observations that go from I as 1 to n. I'm going to multiply x times y for each of those observations and then take the sample mean of that quantity. Okay, so that's this term. Distribute again to the beta naught term. Now here this beta naught term has an xi on it, right, coming from this distributing this xi on the outside here. So I get this beta 0 term, and then which comes out of the sum, and the xi term, which becomes a sample mean. And then xi times xi in the same way we did xi times yi, we have the sample mean of x times itself. Okay, and again the beta 1 comes out. So this is a little easier to parse than the summation notation up at the top. So I've just written everything in terms of sample means. Okay. So to solve for beta 1 here, it's beta hat 1, what we'll do is we will multiply this top equation by negative x bar and add it to the bottom. What that's going to do here, we're going to get a negative x bar attached to this term, which is now going to be positive. These two terms are going to cancel. Okay, so this is just elimination to solve a system of linear equations. And so when I do that, so again, what I'm doing is multiplying this top equation times x bar times negative x bar, adding it to the bottom. So I get, this is from this is from the bottom equation, and then y bar times the negative x bar, which I get by doing that manipulation. I have the negative beta 0 x bar comes from the bottom. This one comes from the top equation, as we just described. These things are going to cancel. And these terms are hanging out. This one is from the bottom equation. This one is x. I had x bar. I multiplied times x bar, so I get an x bar squared here. Okay. Note that these are actually different. These x squared bar and x bar squared. Right. So x squared bar is 1 over n sum xi squared. Right. This is the sample mean of the squares. Okay. This term is the square of the sample mean. So this is 1 over n sum xi squared, right? So these terms are actually different. But that's what the sample mean notation is doing. Okay, so canceling this term, we're left with the following, and then we can solve for beta 1 by factoring it out and pushing this terms on the other side, dividing over by the x squared bar minus x bar squared. So we're left with this. Okay. Yay. Lots of algebra here. Just keeping track of it to be thorough. Not exactly super difficult, but just setting up a bunch of equations and solving them. This is what we have for beta 1 hat. Okay. So this is the best slope coefficient in terms of minimizing the empirical mean squared error. Okay. So let's go back. So if this is our beta hat term, we can go back to this equation, which is one of our normal equations, and we can plug in our estimate for beta hat 1, which we know, and we can use that to solve for beta hat 0. So this is beta hat 0 is y bar minus beta hat 1 x1, where we know what beta hat 1 is, so this allows us to completely know beta hat 0. Right? This term can be plugged in down here, and that's it. Okay. So yeah, this is our these are our coefficients. So congratulations, we've solved for the best slope and intercept here. But we're actually going to do a little bit of simplification here, because what we've done is just sort of crunch through some algebra, but we don't see any intuition for, with these expressions anyways, it's hard to see, what kind of x and y, for example, makes it so that beta 1 hat is large? What kind of x and y makes it so that beta 0 is large, right? It's hard to parse what these actually mean. We just did some algebra. So let's do that, and in order to do that, we're going to rewrite these expressions into easier to parse terms. So first, we're going to rewrite this numerator, and actually this denominator as well, using the following fact. Okay, so the fact is that xy bar minus x bar y bar is equal to this expression. Okay, so this is going to allow us to substitute, to get rid of this mean of the product times product of the means with this expression here. So why is this true? Well, we can just do some expansion and show it. If you go ahead and FOIL this term, you get the following, and then you can distribute the sample mean across all the terms here. You get, this is a constant, doesn't depend on I. This is a constant, doesn't depend on I. This is a constant, doesn't depend on I. So you can just distribute, and you get the following. This x bar y bar cancels, and you get exactly what we were hoping. So this is this expression is x y bar minus x bar y bar. Okay. So using the fact, and this again is our estimates of the slope and the intercept. So using the fact, we'll rewrite the slope term as this product here. This is xi minus x bar, yi minus y bar over, and here I'm actually applying the same property, but just for y equals x, right? So here, this is the same as this, but where y equals x, right? So I'm going to apply this same rule to the denominator, just setting y equal x. Okay. So we can cancel these front terms if we wish. We can divide the numerator and the denominator by n minus 1 and set it by n if we wish. Why would we want to do this last thing? Well, does anybody recognize this term or this term? Yes, I can hear those of you who are screaming into your microphones. This is the sample variance of x squared, right? This is when we divide by 1 over n minus 1, we get the sample variance, and this on top here is the sample covariance, the sample covariance between x and y. Okay, so we can write it as the 1 over n. This is natural, but we can cancel. Right, we can cancel this, write it as nothing out in front, or we can write the 1 over n minus 1 out front because they'll cancel as well. This is nice, this writing, because we recognize a sample covariance and a sample variance. Okay, so let's summarize. So we have the sample covariance, excuse me, and sample variance. Recall this is the definition of sample covariance and sample variance, which I hope you've seen in your stats courses. This 1 over n minus 1 is conventional. It is a little less conventional, but sometimes happens that people will define sample covariance or variance with this 1 over n out front. Because we're going to see these different kind of ideas where we're dividing by something n minus some number, n minus some number, we're going to introduce special notation for it. So this is an unbiased version. I'll talk about what that means in a little bit, but this is when we divide by the 1 over n minus 1, we denote it as s, and when we divide by n, we're going to denote it as sigma hat. Right? They're both estimates of this sigma. So they're both estimates of sigma squared in this case, right? For the variances. So we either denote them s if we're dividing by n minus 1, or sigma hat if we're dividing by n. So that is notation, and what we've seen via these reductions is that we can write the slope term as, we can do the covariance with divided by n over the variance divided by n, the covariance divided by n minus 1 over the variance divided by n minus 1, or just cancel the n minus 1s or n's respectively and just write it as these sum terms. Okay, these are all equivalent, and then beta 0. We haven't really manipulated it. It just hangs along as we've found its solution to be this. Okay. So why is this nice? Well, we can look at this beta 1 hat and we can say, all right, what happens if variance of x, I don't know, let's say the sample variance of x is 6, and we increase the covariance between them. So we fix the variance at some number, I just picked 6. We increase the variance, the covariance. What's going to happen is, as you increase the covariance and leave the variance fixed, the slope here is going to get larger, right? So this is an intuitive way for us to relate this estimate of the slope in a simple linear regression problem to quantities which we know, that is the sample variance and the sample covariance. Okay. So we have not actually, there's a lingering question here, in that we've only showed that these beta hats, by beta hats I mean the beta hat 0 and beta hat 1, we've only showed that they're critical points. That is, you take their derivatives, set them equal to 0, solved. Why are they in fact minimizers and not maximizers or a saddle point? Well, you can grab a calculus text and convince yourself of this. We are just going to sort of take it and run. So they are indeed minimizers, but we're going to move on to other exciting properties of these estimates. Okay. So this slide I was just talking through informally already. So the idea that as we increase the sample covariance for fixed sample variance of x, we get larger slope term. If we kept the covariance fixed and increased the sample variance, the slope term would go to 0, right? If, for example, their covariance was negative, right, we would see a negative coefficient. So it's kind of interesting because this thing here, right, this is always positive. It's a variance, or positive. It's always non-zero. In an extremely boring case where everything is constant, you can have 0 sample variance. But this is always non-negative. This term is positive or negative. So the sign of the slope here is completely dependent on the sign of the sample covariance, right? because the sign is not affected by the sample variance. That's just an interesting property we can see here. Okay. So how to actually interpret these even more. So the intercept, if we look at this expression here, so this is the conditional mean of y given x is, this is what we've assumed here, that it's a simple linear regression case, which we estimate with these beta hat terms. Okay. Well, the intercept, what's the intercept? The intercept is, if we plug in x equals 0, we get the intercept, right? So the intercept is an estimate of the expectation of y once I fixed x to be 0, right? So I fix x equals 0, this beta hat term is an estimate of the expectation of y, right? That's one interpretation. An interpretation of the slope, well, remember slope is rise over run. What it means is that as x increases 1 unit, whatever the units are of x, as x increases 1 unit, right, how much does the expectation of y given x increase? Well, that is beta hat 1, the slope term. Okay, you can convince yourself of that by just taking the difference of this expression and this expression where x is x plus 1. Right? So for 1 unit increase in x, we would expect 1 unit increase in the expected value of y given x. Okay. So along those lines, let's consider an example. So the example is the following. So consider a regression problem where x is the height of mercury on a thermometer and y is the ambient temperature. So we're going to predict temperature from height of mercury. Right? That's something that's a well-known principle that we use to build thermometers. And so let's say we have some data and we have an estimate beta 1 hat. Okay. So here's a question: how much do we expect the temperature to rise if we artificially increase the height of the mercury by 1 unit? Okay. So let's think about this. So we artificially increase the height of the mercury by 1 unit. How much do we expect the temperature to rise? Okay. Well, you're thinking about this slope. You're thinking about, well, when x increases by 1 unit, y should increase by the slope term, right? Beta hat 1. But here's a key point here, and this is just a little bit of a trick, so I apologize for being a little bit devious, but I want to make my point here. If we artificially increase the height of the mercury by 1 unit, what happens? Like, for example, if I pour extra mercury into the thermometer, what happens to the temperature? Right? I can record a new x, it's going to be higher. The answer here is nothing. Okay? And I just want to make this point because we are estimating some relationship between variables, but we're actually not estimating anything about causality. So when I add this extra condition in here artificially, sort of changing the relationship between x and y when I step in and do something manually, right? If I was just going to observe that the height of the mercury increased by 1 unit sort of naturally, I would expect, okay, given my previous information, I would expect that the temperature would increase by the slope beta 1 hat, right? But there's this key relationship, this key fact here that if I jump in and I say, I've artificially done this, I'm sort of manipulating it, we don't know if the previous relationship between y and x holds when I come in and do something manually, right? So this artificial is important, and in general, we actually don't say anything about causality, right? For causality here, what we're saying is this would be a causal relationship if the height of the mercury was causing the temperature to be high, right? If that was true, I could increase the height of the mercury however I wanted, and the temperature would go up. But we are not saying anything about causality, okay? We are just saying, I see a bunch of observations, something's going on between y and x, I don't know which one causes the other or if there's any causal relationship between them, and I want to predict y from x. So we are not saying anything about causality. Please use common sense here. I think people are initially a little bit thinking mathematically, as they should when they're seeing these new tools, and they think, okay, here's what this means. I increase x, I get increase y. Not necessarily because perhaps the intervention, whatever intervention that you stage in order to increase x, is actually changing the relationship between x and y, right? And in general, y is not caused by x. So I will get off my soapbox here and hope that I've made my point. All right, so how to actually do simple linear regression in R. We're going to do it with this syntax LM, which is linear model, y, and this notation, you may have seen this in previous courses, but this is y as a function of x. So this will regress y onto x. And the result is a list, with a lot of information in it. We're going to break down what it does sort of piece by piece. So there's a lot of things stored in this LM, which we'll get to later. But you can access the coefficients, these beta 0 and beta 1 terms, with either coefficients applied to this LM or coef applied to this LM. Detailed information, which we'll break down in more detail in future lectures, can be found by running summary on the output of this LM. And with that, I will actually turn to R, and we will have our first R tutorial in this course. For those of you who appreciate getting your hands on applied problems, you're probably really ready for it. In general, we're going to have more R code tutorials than we've had for this first couple lectures, but since we were introducing concepts first, we didn't do that much code, but now we will. So what we're actually going to revisit here is remember the voting example that we had in the previous lecture. So this idea where we had where we were looking at different models and how flexible were they? Were they good models or bad models? But we were predicting the percentage Trump vote in different regions in the 2016 election using how much of different sports people are searching with their internet traffic. Okay, so this is going to be revisiting that data set. I got that data set from this 538 package. 538 is a great news outlet slash data analysis site. They do a bunch of different things. They're sort of technically minded news outlet, and they make an R package. So I'm going to install this package 538. You only have to do this once, and then I'm going to load it. Okay, and I'm going to load this NFL fandom Google. This is the name of the data set. Okay. So I'm going to attach the data set. When I run attach, that just means that I can refer to a column by name instead of having to do data frame column. So attaching the data set. And then this is something, don't run this. This is something that I used for just to save this as a CSV so I could access it later. All right, so what are the column names of this data set? So the names of this data set, I just ran call names, and I see the following. So I have Trump 2016 vote as one of my columns. I have college football, college basketball, NASCAR, NHL, Major League Baseball, so on and so forth. Oops. All right. So we have a bunch of different sports. Recall in the lecture, we've only used a few of these. We used NFL, we used NBA, we used MLB, and we used NASCAR. So there's more columns in here from before, but remember this is the percentage of Google search traffic for different regions. I don't remember what, DMA is the designated metropolitan area, so it's the name of the city or region that the data pertains to. Okay, and so let's look at a quick plot here. This is just a scatter plot of NASCAR traffic. We found that NASCAR traffic was kind of interesting because it seemed to have a strong relationship with percent of voters in the area who voted for Trump. So we have NASCAR traffic along the x-axis. Along the y-axis, we have percent Trump vote. We see this is the relationship we saw on the slides, that as you increase NASCAR traffic searching, you're going to see a higher percentage of people in the region voting for Trump in 2016. Okay. So let's compute the least squares estimator. Okay. So I'm going to compute the least squares estimator. Remember from the slides, so beta 1 hat, this is just keeping with my notation from the slides, it is the covariance divided by the variance. Okay, and what is the variance? This is the variance of x, right? So the covariance between y and x divided by the variance of x. Okay, and these are all sample, obviously, because we're working with data. So this is going to be my beta 1 hat. Okay. Once I have beta 1 hat, I can actually, let me just pull this up real quick so we can remind ourselves. Once I have beta 1 hat, so what I've done is I'm finding beta 1 hat as this expression, and then beta 0 hat, I can plug in beta 1 hat and the sample means of x and y. So this is the sample mean of y minus beta 1 hat times the sample mean of x. So I can do that. This is beta 0 hat, sample mean of y, minus beta 1 hat times the sample mean of x. And I can add this line to my plot. So I'll add this to my plot using the AB line function, which takes a slope, an intercept for A and a slope for B, added as a green line. There it is. So this is my least squares line. And here we have it in green. I'll add a quick legend, which shows me that the least squares line is here in green. Okay. So this was computing the slopes and the intercept manually. To compute it using R, I'll use LM, as we discussed in the slides. Okay. So LM, I will give LM y as a function of x, like I mentioned in the slides. I'm going to give an extra argument, which is the data frame that these y's and x's are coming from. So when I run this, it just prints my what I called, and it prints the beta 0 hat and the beta 1, the intercept and the slope. So let's just compare quickly. So this was the coefficients that R gives me. What about, how do they compare to the estimates that I did by hand? So beta 1 hat, beta 0 hat. So I have exactly the same, subject to rounding for 3 decimal places. Okay. These are the same estimates. This is unsurprising because R is doing exactly what I just did above behind the scenes here. So I can save this LM object as a, so I'm gonna give it a name and save the output of this LM. And then, this is neat, instead of specifying an A and a B, I can just do AB line and give it an LM object. Okay, so pay attention to this plot over here. It's gonna go from green to red because I just superimposed the same line because it was the same coefficients on top of it. Okay. This is also the least squares line. Okay. How about computing the mean squared error? Okay, so remember we talked about mean squared error. I'm going to actually separate the data into a training set and a testing set. Remember, the reason we do that is we want to avoid overtraining. It's going to be hard to overtrain with this simple line here, but the principles are solid, and so we're just going to start establishing some best practices. So what I'm going to do here is I'm going to have a training set. Okay, so my training set, I'm going to select training indices by sampling from the number of rows in the data set. I'm going to sample 80% of the rows. Okay, so this is selecting 80% of the rows, and then I'm going to grab those rows, set my training set. Everything else is going to be my testing set. Okay. So I have originally I have 207 observations. I put 165 into the training set, 42 into the testing set. So now when I build my linear model, I'm going to use data equals train instead of data equals all the data. Okay. I have my training residuals. My training residuals I can get by saying true y minus the predicted y. And this predict is important. So predict function, we're going to see as we go later in the course, but the predict function can be kind of finicky. But if you apply predict to a linear model, it will predict on the X data used to build the model. So this gives me the prediction on the training set that was used to build the model. So my training, and by training e's here I mean training residuals. Okay, mean squared error is the mean of the square residuals. And then I'm going to do exactly the same thing for the testing residuals. So here I have the testing residuals. And then instead of just being able to run predict, I have to tell predict, hey, don't predict based on what you used to build the model. Here's the new data, the testing data. Okay, so this is data that was not used to build the model. I get a testing mean squared error, a training mean squared error, and a testing mean squared error. So my testing mean squared error is a little larger. We don't read too much into that, just because we can see sort of visually here, we have the benefit of looking at this graphic and seeing that we're not overtraining, but just due to random chance, the testing MSE is a little bit larger than the training MSE. In general, that might be something where it would raise cause for concern, and we would say, maybe look into, is your model too flexible and honing into artifacts of the training set. For this model, we're not too concerned about it because it's a simple linear regression model, but in general, comparing training MSE and testing MSE, especially as you increase the flexibility of the model and see what happens to the training and testing MSE, is good practice. Okay. And so let's just plot on here. So I'm going to scratch this plot and start another one. Here's the training set. Here's the testing set, the red triangles. And here is the linear model built from the training set. All right, and so that's what I have here. I have a little encouragement at the end of this R code. So this R code is posted on the Course Sakai site, but you can. I encourage you to do the same with the MBA traffic, just to get yourself comfortable with this code, and because there's sort of a lot going on here with training MSE and all these sort of things. Okay, so let's jump back to the slides. I believe I have only one or two more slides here. So the last thing I want to say is simple linear regression in Python. And I know this is an R course. Maybe some of your heart stopped when I mentioned Python in a course that we're going to be using R. But I'm only mentioning this because it's something that I think just needs to be mentioned at least once. And that is, I've had students that I've worked with tell me in the past, I know a lot of Python, I'm very comfortable in Python, but because I'm taking all my statistics classes in R, I know how to analyze it in R, but I'm more comfortable doing other things like cleaning data in Python. Okay, for me, this is nuts because both tools can be used. We're using R because R is catered to statistical analysis. What that means is that sort of you don't have to deal with the object-oriented syntax and all these sort of things. It's sort of a clearer path from the concepts to applying it in R. But if you're working in Python, Python can do linear models. The interface is object-oriented, so if you're very comfortable with object-oriented interfaces where you do like, object dot something, that's what you're going to see if you're doing linear models in Python. In general, the tools for inference, they're less because people who work in Python tend to be more computer scientists and less statisticians. But prediction often works very well. The machine learning community really likes Python. Lastly, just philosophical, sort of hinted at this. R, being built for statistical computing, sort of operates on a data-first paradigm. That means thinking about doing statistics first and foremost is its goal. Python is first and foremost a general programming language, so it has this object-oriented first paradigm. So you'll see those philosophy differences. And I don't say any of these things to disparage Python. I use Python a lot myself. It's a very nice language. I like to use Python for generality. If I'm doing something specifically in R, I'm working on a project where I'm doing statistics or data analysis almost exclusively, and then if I'm working with machine learning, especially doing things like neural networks, the software is better in Python, so I switch back and forth between them. But we can do linear regression in Python. I'm going to show you this once, so we've all seen it. But here is an example. And this is not going to be something that's going to be tested on or required to know. So just hang out and listen, and hopefully learn something. So how would we do linear models in Python? Well, in sklearn is scikit-learn. It's a very popular machine learning package in Python. We're going to import linear regression. We're going to import a couple of other packages. Pandas you recognize, NumPy you recognize, Matplotlib you recognize. Seaborn, if you haven't seen it, helps Matplotlib do statistical graphics in a way that looks pretty by default. And then this Patsy package is one that allows you to write R formulas with this y tilde x, which is nice. It allows you to write them in Python. Okay, so the vote data, I'm going to load this this voting data. This is exactly the same data we were looking at in R, and what I see here is running head on this data frame. I see metropolitan area, all these different numbers, right? This Trump vote, and this is the percentage of Google traffic related to the different sports. Okay. I'm going to do this outcome predictors is D matrices. So this is some Patsy stuff where I'm parsing y as a function of x using data equals vote data. Okay, this allows me to build predictors and an outcome. And then I'm going to fit the linear model. I'm going to declare LM as a linear regression and fit these predictors on fit a model using these predictors in this outcome. Okay, I get the coefficients. Quick question: do these coefficients match what we saw in R? Well, we hope so. Let's double check. So in R, we have that beta 1 0 and beta 1 hat are uh, 3.71 and 2.94. So yes, they do match. And then we can just continue on making a plot, just as we did in R, making a scatter plot of the data, and then plotting the linear model, which is slope times the x plus the intercept. And we see similar to what we had in R. Okay, we can predict, similar syntax, but yeah. So I just want to say you can do linear regression in R. Different packages. If you're working in something in Python and you want to do linear regression, you don't have to convert everything to R. It can be done, and that will be the last bit of Python we will discuss in this course. But I wanted to say that it can be done, and don't limit yourself. Okay, so that's all I have for this lecture, and I look forward to seeing everybody next time.